Today we're going to get unsafe, and this shirt is entirely too safe. Cat with a laser gun riding a dinosaur, I think we're on theme now. Arguably, the main reason you'd want to pick up Rust over any other compiled language is that Rust keeps you safe. But what does that mean? When you write a program in a compiled high-level language like Rust, C, C++, Zig, etc., it's converted into low-level instructions for processors. These instructions are very direct. They move data from one register to another, add, subtract, shift bits, and so on. There are no restrictions on what those low-level instructions can do, which means you can do things that might result in unexpected or undefined behavior. This is what we consider to be unsafe. For example, in low-level languages that instruct processors directly, there's nothing stopping you reading and writing to the same memory location at the same time from different threads. See our threads video on why that's bad. Using any high-level language allows us to abstract this behavior in ways that are easier for us to understand. All compiled languages go further than just making the instructions easier to read and write though. They also enforce their own rules as to how they're used. Rust with its ownership rules and borrow checker is just one example of how compiled languages make sure that we, the software engineers, don't ask the computer to do anything that could be unsafe. To the best of its ability, Rust will check that your code is safe, but if it only let you do things that it could prove are safe, you'd be cut off from making a lot of programs. This series is accompanied by a free book. Check the description for a link straight to this chapter. My name is Daniel. Welcome to Iris. Sometimes when we use Rust, we need to access heap memory, use peripherals, talk to other software, or even dip into those specific processor instructions we just mentioned. We can't guarantee that any of these actions are safe though. But wait, haven't we been accessing heap memory throughout this series? Why yes. Yes we have. Types like vec and string use the heap to store their data. They take responsibility for and abstract away any unsafe work, meaning that using those types is safe. As a Rust engineer, depending on the type of project you're working on, most of the time you won't personally need to worry about unsafe Rust. You can get by with using other people's code and APIs like the standard library. The point of this video isn't to prepare you to write lots of unsafe Rust, it's to make you feel comfortable with the odd occasion you might need to touch it. We often talk about memory in programming as if it's a single thing, but our programs subdivide memory into three main types of usages, each of which has different pros and cons. Stack memory is where all variables live. Kind of. It's fast because the entire stack is pre-allocated when your program runs, but there are some catches. First, it's actually quite limited. When your program starts, it's given an amount of memory that you cannot specify ahead of time and you cannot change. It's usually 2 megabytes, but you might find it's even less on targets such as embedded devices. If you use more than this small amount of memory, your program will crash. Second, the data stored on the stack must be of known size at compile time. You don't really need to worry about why this is, only that data on the stack cannot change in size. But we've stored lots of things in variables that have variable size, right? Strings, vecs, hash maps, etc. The data for these types is not stored in the variable. What typically happens is that the data we care about is stored on the heap, and that data's location and some other metadata, all of which is of known size, is stored on the stack. Semantically, it's probably fine to say that the variable contains the data. People will always know what you mean. However, for this video, we really need to differentiate what is on the stack and what isn't. In this example, number example stores the actual number on the stack, since it's of known size, 32 bits unless otherwise specified. String example, however, contains the location of the string data, not the data itself, which is stored on the heap. We'll talk about how it gets to the heap shortly. The heap is where we can store things of arbitrary size, and we can usually store things far larger than the entire stack there. Heap memory is allocated on request and freed once you're done using it. Technically, we can't resize heap allocations either, but we can request new, larger portions of heap memory, copy our old data there, free the old memory, and add more things in the new location until we run out of space again. So it's bigger and more flexible than the stack, but it also has some downsides. It's much slower than stack memory because allocating and freeing the memory takes time. Allocation and freeing in Rust is usually handled by the standard library, and other than what we're going to discuss in this chapter, you almost never need to think about that process. But it's not free. Sidebar: once heap memory is allocated, it's almost free to use, with the only overhead essentially being the redirection from the stack to the heap in O1 time. For this reason, some software and languages will actually allocate large amounts of memory called page files that can store a lot of different things at once. This can be done in Rust too, but again there are pros and cons and it's far outside the scope of this video. There's a third kind of memory we don't really talk about as much, but it might be the most important. Static memory is where all values and data you write into your program are initially stored, though frequently they're subsequently moved somewhere else. For example, in this program, data for const example remains in static memory, but const example itself is a reference to that data. See the ampersand. 42 and this is string data 2 are also initially stored in static memory. However, 42 is copied to the stack in number example, whereas this is string data 2 is cloned onto the heap and the location of the data is stored in string example. Differentiating where things are stored is about to become very important, and cough, it's easy to make mistakes if we don't differentiate between the stack, the heap, and static memory. I really can't stress this enough, as it might be one of the greatest misconceptions about Rust. Unsafe Rust does not turn off any Rust safety measures. It turns on tools that Rust cannot guarantee are safe, so you need to make extra certain that you are using them safely. For example, in safe Rust we use references. These are similar to pointers in other languages which point to a location in memory, but references are not pointers. The validity of a pointer cannot be checked, but in Rust, a reference abides by rules that guarantee its validity at compile time before the program even runs. In unsafe Rust, we can access pointers too, but references must still abide by the rules of the borrow checker. Most of these unsafe tools exist in other commonly used compiled languages that have been around for decades and are still rightly very popular today. In many of these languages, these tools are available at any time. Having the tools is not a bad thing. They're necessary tools that we use to do things that there is no other way to do. By making you explicitly opt into these tools though, Rust forces you to really think about how you're using them. Anytime we use unsafe code, we need to wrap it inside an unsafe block. This code uses an unsafe block to call a function that is itself marked as unsafe. Because the function is marked as unsafe, it can only be called within an unsafe block. However, even within that function, code is still treated as safe until you use another unsafe block. This helps constrain unsafe code even further. We'll talk about why you might mark functions as unsafe further on, but what's with all the comments? This is not necessarily a widely used practice, but maybe it should be. The Rust standard library team, who have to work with unsafe a lot, have standardized around making safety communication almost contractual. Prior to the unsafe block, the first thing we see is a safety comment. This tells the reader how the author made sure the code was safe. This may seem odd. If the code is provably safe, why do we need unsafe at all? Unsafe turns on language features that can't be proved safe by the compiler, but that's no excuse for writing unsafe code unsafely. The safety section of the doc comment on the function "this code is unsafe" is used to tell consumers of the function how to use it safely. What you'll often find is that safety comments should mirror the safety section of the doc comments to show that the code follows the guidelines laid out. We've got a whole section on unsafe functions later. The practice of writing a safety comment ensures that when we write unsafe code, we think hard about how we know this code isn't going to hurt us later. Documenting how we know this code is safe is crucial. You can read more about this practice in the official Standard Library Developers Guide linked in the description. One of the main reasons you might want to dip into unsafe Rust is to communicate with memory directly. Rust's abstractions around memory are powerful, usually free or otherwise cheap, and very flexible, but they don't cover every possible need. You may have a use case where you need to talk to memory without going through Rust's abstractions, and Rust lets you do that by turning on its unsafe features to access raw pointers. We usually use references in Rust as if they were pointers, pointing to something that's actually stored elsewhere. But while references include features that make them safe to use, a pointer is essentially just a number that is an address to a location in memory. When you allocate heap data, even in Rust, the operating system provides you with a pointer to the location where the memory was allocated. If we just used a pointer, it would still contain the numeric address of that location, even if we subsequently told the operating system to free that memory. Programmatically, we have no way to know if that location is still ours to use later. Using that pointer after the memory is freed would be an error and is the root of an extremely common bug that you might have heard of called use after free. In fact, because we don't know from just the pointer whether the memory was freed or not, we might even try to free the memory again, leading to another bug called double free. References help us avoid that because we can track their use at compile time, helping us make sure that they're always valid even before we run the code. But the operating system doesn't use references. Actually, references can't be used between any two pieces of software because of their compile time nature. We can, however, share pointer locations. So even in Rust, pointers are being used all of the time, whether we see them or not. Sometimes we may even need to use pointers directly ourselves. You can actually get pointers in safe Rust using &raw const, or for pointers to mutable data, &raw mute. If we run this program several times, you'll see we get a different number every time. One cool thing worth pointing out though is that Rust even types your pointers, including whether the data there is mutable, making it harder to mess things up later. An immutable pointer to an i32 has the type *const i32. Remember, in some circumstances, the variable you're accessing the data through does not contain the actual data. Strings are a good example of this. The pointer to the variable does not point to the string data, it points to the metadata, which itself contains a pointer to the string data. We can access the pointer to the data via a method on the string. Again, there's nothing unsafe about doing this, we're just reading a numeric value that is definitely valid at the time we do it. So getting pointers is perfectly safe. What we can't do is use those pointers to get the data stored at that location in safe Rust. For that, we need to dip into unsafe. Here, we dereference the pointer to go back from the location to the data that's stored there. This is unsafe because Rust can't confirm the validity of the pointer when we do it, it's just some number. Without us checking manually, pointer could outlive the answer, after which, what is pointer pointing at? When we write code, we regularly break it up into small, reusable chunks known as functions. You are at this point, I hope, very familiar with this idea. So far, we've demonstrated that we can place unsafe code inside a block to encapsulate unsafe behavior. This means you can write unsafe code inside a function as long as you write the function in such a way to make sure there's no risk, meaning for someone calling the function, that function is safe. A good example of this is stud mem swap, which swaps the values at two mutable locations. Because swap guarantees the types are the same and through using mutable references knows nothing else is accessing the memory while it does its thing, conceptually this function is safe, even if the very first thing it does internally is run unsafe code. This is what we call a safe abstraction around unsafe code. But that's not always possible. Sometimes the very concept a function or method represents is unsafe. Let's say that through arbitrary means we've got a pointer to some heap data that we know represents a string. We know how long the string is and how much memory at that location is ours. We want to take ownership of that memory and turn it into a string type. We can use the from_raw_parts static method to build a string directly from memory, but the entire concept of manually creating a string like this is unsafe. Firstly, something else likely manages that heap memory. If we create a string from it, we're going to take joint ownership of the heap data, and when our string goes out of scope, Rust will try to free it. How do we prevent a double free when the thing that originally created the data also wants to free it? Secondly, from_raw_parts takes a pointer, a length, and a capacity, none of which can be validated at compile time. And string will cause a reallocation if the capacity is filled, causing us another problem to look out for. Luckily, by being aware of the problems ahead of time, we can still use this function safely. We'll manually make sure our string never exceeds 100 bytes. A little side note, the string may be created with more than 100 bytes, but we will own the entire actual capacity and need to free it when we're done. From_raw_parts is an unsafe method, so can only be called inside an unsafe block. I'm intentionally calling it with a length less than the original string to make a point. Before we do anything else, we're going to prevent overlapping string from being dropped, which would otherwise cause a double free when original string is dropped later. We could prevent original string from being dropped instead, but to me, it makes sense to have this behavior in the inner code block. Counterintuitively, the manually drop type is actually safe. Although it prevents the memory being freed and could result in memory leaks, that's not considered unsafe in the same way as other things in this video. Just be careful using it. Here, we're going to check that the string is what we expect it to be. Due to giving it a smaller length, we only see the first part of the original string. We can push data onto the end of the string and it will correctly change the string. But look how they massacred our boy. It's not unusual to create an unsafe function but then wrap that function in safe code. Like the example we used earlier, std_mem_swap is safe even though the first thing it does is call an unsafe function. Creating safe abstractions might look something like this. We have a conceptually unsafe function that does some work. Ideally, we'd create a safe abstraction, a function that is safe to call by doing whatever necessary checks. The safe abstraction can then be called from safe code. std_mem_swap does this by simply checking that you passed in mutable references of the same type. That's enough to guarantee what it does is safe. When it comes to traits, if any of a trait's methods are unsafe, then the entire trait is considered unsafe, and so is its implementation. It's actually kind of rare to have to use this feature though. If your trait has an unsafe method but a safe abstraction, you might be able to move the unsafe method to an unsafe function. You're likely to need unsafe traits only when the behavior the trait describes is unsafe. For example, send and sync are automatically applied to all types that are only constructed from types that are also send and sync, but both traits are conceptually unsafe. If your type contains types that are not send and/or sync, then the compiler cannot guarantee safe implementation itself. You can still implement send and sync for your type manually, but it's now up to you to check the implementation is safe, so implementing the traits themselves is unsafe. Unions in software engineering are a way of storing different types in the same section of memory. They're typically broken down into two flavors, tagged and untagged. Tagged simply means the type is part of the data, so you can only access the data as the type that it is. We use tagged unions in Rust all the time, and they're perfectly safe. Enums are tagged unions. They only ever take up as much memory as is taken by the largest data type representable inside them, plus a discrimination value, which differentiates the variance at runtime. The discrimination value is usually represented as an I size, but Rust compilers may use smaller numeric types. Rust also has untagged unions, where the type being used is not part of the data, and you can access the binary values as if they were any listed type. Untagged unions are obviously unsafe, but they provide several useful features, either by allowing you to interrogate the data in different ways, or for working with other programming languages that use untagged unions. Side note, my first attempt at an example for demonstrating untagged unions was an IPv4 address union that used both a 32-bit integer and a 4-byte array. However, with that example, we have to consider endianness, which is the order in which bytes are stored in memory that differs on different computers. This felt like it went too far off topic, however, it's still worth pointing out that when creating unions that share multiple bytes of data, you too may need to consider endianness. In this example, we can interrogate characters as U32s. Creating unions is safe, but reading unions is unsafe. Even in this case, where both U32 and char are 32 bits wide, not all valid U32 values are valid chars, but all chars are valid U32s. Writing values is also safe. When we run the program, we can see that both character and number change. This next example of unsafe is so incredibly unsafe that the only time you're ever likely to use it is if you need insane speed and know exactly what you're doing with the exact hardware you're targeting. You might have heard of assembly, but crucially, it's not one language. Assembly languages are languages that have a near one-to-one relationship with the actual instructions of the CPU you're building for. In this example, you can see a function that takes a number and multiplies it by 6 using assembly. There are two versions of the function. The first works on x86-64 target, which, amongst others, covers most Windows and Linux machines and older Macs. The second works on AArch64 target, which cover all modern Macs, but also some newer Windows and Linux machines. As you can see, apart from mov, the other instructions look very different, but do the same things. For obvious reasons, Rust cannot help keep you safe when you're sending instructions straight to hardware, so assembly is only available within unsafe code. Of all of Rust's unsafe features, this is the one you're least likely to need to touch, but as with the others, it's there if you need it. A lot of the time, you're going to be working with code from other people. Most often, that code will be written in Rust, downloaded as a crate, and combined with your code into a single binary. Sometimes though, you'll want to work with code written in other languages, either by consuming a library written in another language or by building a library that another language can consume. This is done with extern. For compiled languages to interoperate, they need to use an application binary interface. Rust doesn't and probably never will have a stable ABI. Instead, we typically use Cs, though other options also exist. Creating a library that can be consumed by other languages is fairly safe. You define a function that will be made available externally, thus the name. The function itself is safe, exposing it is not. To be made available, the name of the function has to be known. Rust usually mangles its function names to avoid what's called symbol collision, where two things have the same name. To expose the function, we need to know its name, so we need to prevent the mangling, but that means there's a risk of collision. Pre-Rust 2024, preventing mangling was done with the noMangle attribute, but as of Rust 2024, we need to explicitly tell Rust that we understand the dangers. You can also call functions from other libraries if they use a supported ABI too. You do this by linking an extern block to a specific library and then listing the signatures of the functions exposed by that library that you want to use in your code. Everything about this is unsafe. If there's no dynamic library on the target system that shares a name with the linked library, the program will panic. If the function names do not match, the program will panic. If the function names do match, but the signatures don't, you'll get undefined behavior, or your program will panic. Nonetheless, the ability to import libraries written in other languages can be a powerful tool in your belt. You probably want to make sure you validate data coming from external code, especially for anything more complex than a number. In older editions of Rust, it was possible to have mutable statics via Unsafe Rust. This would allow you to have mutable global variables that were safe-ish to use so long as they weren't shared between threads. As of Rust 2024, this is no longer the case. If you don't mind sacrificing a tiny bit of speed, the same thing can be achieved through safe abstractions and tools like atomic types or interior mutability. If you really need the speed, then you can still fall back on raw pointers. At the end of the day though, mutable globals are a bit of a crutch and should generally be avoided where possible, and I think there's a lesson here. Anytime you find yourself reaching for unsafe code, you want to be sure that there are no other acceptable ways to do the same thing. Unsafe Rust can speed up your code and can let you do things there's no other way of doing, but you should assess the various possibilities and trade-offs of alternatives before committing to unsafe. Even if you have to use unsafe code, are there existing abstractions for what you're attempting in the standard library or other well-tested crates? You shouldn't be afraid of unsafe, but you should understand that it's going to turn on features that you are responsible for making sure are used safely. If you don't need them, don't use them. Outside of specialist use cases, you're unlikely to have to write much, if any, unsafe code yourself. Nonetheless, hopefully after this video you see that it's not as scary as it seems. You still have all the normal safety checks, but now you have additional features you can't get otherwise. And now you know a bit more about what to look for to keep yourself safe when the compiler can no longer help. If you are going to be writing unsafe Rust, there's a tool called wirh that will, in your running code, help you detect potentially undefined behavior that you might have missed. It's not a panacea, it can't catch everything, but it is a final potential safety net that you should use to protect yourself. We're going to lean into pretty much everything we've learned so far to learn async Rust. This is going to be a bit of a unique video. We'll go deeper than you generally need to go in our exploration of the space. Typically, you'd grab a crate like Tokyo or Async Stud to do all the hard stuff for you. By learning the core concepts, you should come out of the other side with a much better idea of how async works under the hood. As with this video, you may never need to write any of the complex stuff, but it should help you feel more comfortable with what I think many would agree is the last remaining truly sharp edge of Rust programming. So if that excites you, then I'll see you next time. Today we're going to get unsafe, and this shirt is entirely too safe. Such a stupid joke.